Picture yourself on a transatlantic flight at 39,000 feet. Suddenly, the engines sputter. The cabin goes silent. The airline tried using automotive gasoline instead of jet fuel. This sounds like fiction, but the physics behind why it would be catastrophic is terrifyingly real. Every aircraft refuses to touch gasoline for a reason. This is Sky Secrets, and today we are uncovering one of the most critical yet misunderstood aspects of aviation. Jet fuel and gasoline look similar. They both burn. So why does aviation spend billions on specialized fuel when gasoline is everywhere? The answer involves physics and engineering that keeps you alive every single flight. Aviation fuel is engineered for extreme conditions gasoline cannot handle. At cruising altitude, temperatures drop to -60 degrees Celsius. Gasoline would freeze or create vapor locks that kill engines. Jet A1 has a freezing point of -47 degrees with ice prevention additives. This is the difference between landing safely and falling from the sky. Let me start with something that will blow your mind. Gasoline and jet fuel both come from the same source, crude oil. They are both petroleum products. They both combust. They both release energy. So why the massive difference in application? The answer lies in molecular structure and refining process. Gasoline is a lighter fraction of crude oil. It contains hydrocarbons with 5 to 12 carbon atoms per molecule. This makes it incredibly volatile. It evaporates quickly at room temperature. You can smell gasoline from across a parking lot because its molecules escape into the air constantly. This volatility is perfect for car engines that operate at ground level with consistent atmospheric pressure. Jet fuel, specifically Jet A1, is a heavier fraction with 10 to 16 carbon atoms per molecule. It is essentially refined kerosene. This makes it far less volatile. It does not evaporate easily. It remains stable across extreme temperature ranges. And this stability is not a luxury in aviation. It is an absolute necessity. Here is the critical difference. When you drive your car, the engine operates in a relatively stable environment. Temperature might range from -10 degrees Celsius in winter to 40 degrees Celsius in summer. Pressure stays roughly constant at sea level. Your fuel system never experiences dramatic shifts. But an aircraft, it takes off from a hot tarmac in Dubai where ground temperatures hit 50 degrees Celsius. Within 30 minutes it climbs to 40,000 feet where outside air temperature plummets to -60 degrees Celsius. The fuel inside the wings experiences this same temperature swing. Gasoline would catastrophically fail under these conditions, and I am going to show you exactly how. Imagine this scenario. An airline decides to cut costs by using automotive gasoline. The aircraft takes off normally. Everything seems fine during climb. But as the plane reaches cruising altitude, something terrifying begins to happen inside the fuel tanks. Gasoline has a freezing point of approximately -40 degrees Celsius. At 40,000 feet where commercial jets cruise, ambient temperature regularly drops below -50 degrees Celsius. The fuel inside the wings starts to crystallize. Not completely solid but forming ice crystals and slush. These ice crystals begin clogging fuel filters. The fuel pumps struggle to move the increasingly thick liquid. Flow rate to the engines decreases. The engines, which require thousands of liters of fuel per hour, begin to starve. Power output drops, and if the temperature continues to fall, the entire fuel system could freeze completely. Now contrast this with Jet A1. It has a freezing point of -47 degrees Celsius. This might not seem like a huge difference, but it is engineered to remain liquid even when outside temperatures drop to -60 degrees. Why? Because the fuel inside the tanks does not get as cold as the outside air. The fuel acts as a heat sink, absorbing warmth from the engines and cabin systems. But there is more. Jet fuel contains additives called fuel system icing inhibitor, known in the industry as anti-icing additives. These chemicals prevent ice crystal formation even when fuel temperature approaches its freezing point. Without these additives, even jet fuel could cause problems. With gasoline, you would not even have the option of adding them because the base fuel is fundamentally unsuitable. Airlines track fuel temperature throughout every flight. If fuel temperature approaches -40 degrees Celsius, pilots must descend to warmer altitudes or increase speed to generate more heat. This is standard operating procedure. With gasoline, this procedure would be useless because you would hit critical temperature much sooner. Here is another killer problem with gasoline at altitude, something called vapor lock. This is when liquid fuel turns into vapor inside fuel lines before reaching the engine. Let me explain why this is catastrophic. Gasoline has a very low flash point, around -43 degrees Celsius. Flash point is the temperature at which fuel gives off enough vapor to ignite. Low flash point means high volatility. In your car, this is fine. Fuel pumps are designed to handle some vapor. Pressure stays consistent, but in an aircraft, atmospheric pressure decreases dramatically with altitude. At 40,000 feet, atmospheric pressure is only about 20% of sea level pressure. This lower pressure causes liquids to vaporize much more easily. Gasoline, already highly volatile, would begin boiling and turning into vapor inside the fuel system. When vapor fills the fuel lines instead of liquid, the fuel pumps cannot generate pressure. Engines require liquid fuel injected at high pressure into combustion chambers. Vapor cannot be compressed or injected effectively. The engines flame out, both engines. Simultaneously, you are now in a powerless glider at 40,000 feet with 300 passengers on board. Jet A1 has a flash point of 38 degrees Celsius. This is deliberately high. It means the fuel remains liquid even when pressure drops at altitude. It will not vaporize in the fuel lines. It stays stable, flowable, and pumpable no matter how high you fly. The difference between -43 degrees and +38 degrees might seem arbitrary, but it represents the difference between controllable fuel and explosive vapor. Airlines cannot risk vapor lock. It is non-negotiable. That is why jet fuel is the only option. Now let us talk about energy density, because this is where the economics truly bite. Airlines do not just care about safety, they care about efficiency, range, and profitability. Fuel is the single largest operating cost for any airline, often representing 35 to 40% of total expenses. Gasoline contains approximately 42.7 megajoules of energy per kilogram. Jet A1 contains approximately 43.5 megajoules per kilogram. That is a difference of 0.8 megajoules per kilogram. Sounds tiny, right? But when you are carrying 80,000 kilograms of fuel on a long-haul flight, that difference translates to 64,000 megajoules of additional energy. In practical terms, this means an aircraft running on jet fuel can fly farther on the same weight of fuel. For a Boeing 777 flying from London to Singapore, that extra range could mean the difference between a non-stop flight and a fuel stop in Dubai. Fuel stops cost time, money, landing fees, and passenger satisfaction. But here is something even more critical. Aircraft are weight limited. Maximum takeoff weight is determined by wing lift capacity and structural limits. If you loaded an aircraft with gasoline instead of jet fuel, you would need to carry more fuel by weight to achieve the same range. More fuel weight means less payload capacity. Fewer passengers, less cargo, lower revenue. Let me give you real numbers. A Boeing 777-300 extended range variant can carry up to 181,000 liters of fuel. If that fuel were gasoline, the aircraft would need approximately 8% more volume to match the energy output of jet fuel. But fuel tanks are fixed in size. You cannot just add more volume. The aircraft would simply run out of range. This is why airlines obsess over fuel efficiency. Even a 1% improvement in fuel burn translates to millions of dollars in annual savings. Using gasoline would be like shooting yourself in the foot economically, even if it were physically possible. Let us talk about something terrifying that most passengers never consider: fire and explosion risk. Gasoline is extremely flammable. Its low flash point means it can ignite from a spark, static electricity, or even hot surfaces. In an aircraft, fuel is stored in the wings, right next to engines that operate at temperatures exceeding 600 degrees Celsius. Fuel lines run throughout the fuselage. Electrical systems, hydraulic pumps, and auxiliary power units create heat and potential ignition sources everywhere. Jet fuel is specifically designed to be difficult to ignite. Its high flash point means it will not ignite unless exposed to sustained high temperatures or open flame. This gives engineers and safety systems time to respond to fuel leaks without immediate catastrophic fire. There have been incidents where jet fuel has leaked inside aircraft. In many cases, the leak was discovered and managed before ignition occurred. If that fuel had been gasoline, the outcome would have been drastically different. Gasoline vapor would have filled the cabin or cargo hold, creating an explosive atmosphere. A single spark could destroy the aircraft. Aviation regulators understand this. The Federal Aviation Administration in the United States, the European Union Aviation Safety Agency, and the International Civil Aviation Organization all have strict fuel specifications. These specifications exist because of lessons learned from decades of accidents, testing, and engineering analysis. Gasoline is not banned from aircraft because of tradition. It is banned because using it would result in crashes, deaths, and the collapse of commercial aviation as we know it. Let me share something from aviation history that proves this point. In the early days of jet aviation during the 1950s, engineers experimented with different fuel types. Military aircraft tried using high-octane gasoline in early jet engines. The results were disastrous. One documented case involved an experimental military jet that attempted high-altitude flight using aviation gasoline. As the aircraft climbed above 30,000 feet, fuel flow became erratic. The engines experienced power fluctuations. Ice began forming in fuel filters. The pilot had to abort the mission and return to lower altitude immediately. Another case involved fuel contamination. A small amount of gasoline accidentally mixed with jet fuel during a refueling operation. The aircraft took off normally, but during climb engine performance became unstable. Investigators later determined that the gasoline fraction had vaporized at altitude, creating air pockets in the fuel system. The engine surged and flamed out temporarily before relighting. These incidents are buried in classified military reports and aviation safety databases. They are not publicized because they reveal just how fragile the balance is between safe flight and catastrophe. Commercial aviation learned from these mistakes. That is why fuel quality control is so strict. Every batch of jet fuel is tested before it enters an aircraft. Samples are checked for contamination, water content, freezing point, flash point, and viscosity. If a single parameter is out of specification, the entire batch is rejected. Airlines cannot afford to take risks with fuel. A single fuel-related engine failure could cost hundreds of millions in lawsuits, aircraft damage, and reputation loss. This is why they pay a premium for jet fuel. It is not just fuel. It is insurance. You are about to board your next flight. You will walk through the terminal, scan your boarding pass, and settle into your seat without thinking twice about the fuel in those wings. But now you know the truth, that fuel is standing between you and a catastrophic engine failure at cruising altitude. It is the reason your transatlantic flight does not turn into a glider over the Atlantic Ocean. Aviation does not run on luck. It runs on precision engineering and uncompromising standards. The next time someone asks why planes cost so much to operate, you will know the answer. Because cutting corners on fuel would mean cutting lives short. If you made it this far, you are exactly the kind of person this channel exists for. Someone who asks questions. Someone who wants to understand the systems that most people take for granted. So do me a favor, smash that like button. Subscribe to Sky Secrets and turn on all notifications because we are exposing aviation secrets that will change the way you fly forever. Comment below with your biggest question about aviation. The most interesting one will become our next deep dive investigation. This channel grows because of viewers like you. Let's keep digging deeper together.